Anyway, the program's just about loaded in. It's actually about 4,000 characters long.
It took about 20, 30 seconds or so.
That's right. It's not too bad, but cassettes are slow.
Yeah, there it goes.
Anyway, it's loaded in. Let's run it now. RUN, return. And this program is in fact a simulation of the loading process, of loading a cassette tape as it goes past the playback head on the cassette recorder. And I can start the tape moving, and you can hear the two notes that represent the 0 and the 1 that the computer understands. The high note represents a 1, and the low note represents a 0.
Well, as you said, this is a very slow method of getting stuff into a computer, but it is very, very cheap. Why not? Let's use a disk unit.
That's right, that's a lot faster. We've got here a floppy disk, and it consists of a piece of plastic, rather like the tape used on a cassette. It's inside an envelope, and you have to be careful to protect it. You mustn't scratch that surface, as you have to look after cassettes as well. And that is played through a disk unit. So let's plug that disk unit in. We've got two connections. That first one is the power supply to the disk drive, and the second one is the data lead, or the lead down which the characters come. There, that's plugged in. And we can now plug the floppy disk, or insert the floppy disk into the drive, and we can have a look and see what programs we've got stored on this drive. Ask for a catalogue of the drive. See, there are lots of programs stored.
Oh, it's the whole list of them here, yes.
That's right. Well, let's take one of those and load it in. Load program called Demo 2. Just watch how quick this is. Go.
Again, you could just hear it. It's almost instantaneous. Well, how much faster is it than the cassette?
Well, it's about 100 times faster loading from floppy disk than loading from cassette.
And how much does it cost in comparison?
Well, the comparison is about 7 times more expensive for the drive unit than for an ordinary cassette recorder, but a lot faster. Let's run that program. And as you can see, it generates some high-res colour graphics and some music to go with it.
It's very beautiful. Oh, it's lovely. But to make this into a really complete system, what we need is a printer on it.
That's right. That's certainly the next thing to add on to the system. And we can plug that in again underneath.
And that you'd find on any other micro, you'd always find a printer socket. Yes.
Somewhere to plug a printer in. Now, you'd want a printer really for two reasons. Either because you're developing your own programs and you want to be able to list them out, see what program instructions you've given, or else if you're using the computer as a word processor, you might want to print the letter out after you've written it.
A word processor that really converts into a rather sophisticated typewriter, enables you to correct errors or move paragraphs around without having to retype the whole letter.
That's right, that's right. And the word processor chip itself, or the word processor, isn't held on cassette or on floppy disk, but we've actually got the word processing program on this integrated circuit, this chip.
And that's plugged into the machine, into a socket in the machine?
That's right, we've got one inside like that. And by pushing that key there, we can enable that chip, turn that chip on, and turn it into a word processor. So let's now print out the script of this program. And the script is actually stored on floppy disk. So I'll tell it to print the script out. And you'll see in a moment that's coming from the floppy disk and appearing on the screen. And at the same time, also on the printer over here.
Well, thank you very much, John. Well, different computers may appear to be very different, but deep down, the way the various parts are organised is very much the same with all machines. And it's been like that ever since the earliest computers. And if you look hard enough, some of those old machines are still around. When I think of the design of aircraft, I think of aerodynamics and complex mathematics, particularly in the design of the wing, which is, after all, what keeps the aeroplane in the air. But on a sailing boat, the sails are effectively the wing stuck vertically in the air, and that's what enables the boat to sail against the wind itself. But those sails, they're complex, they're three-dimensional, they're curved in every direction. A flat sail would have the aerodynamics of a brick. Being so complex in their shape, they require very complex mathematics to enable the optimum shape and the optimal design to be made, particularly for professional sails that consistently win races. This is a sail loft at Bruce Banks Sails, one of the largest in the country. It's here that the cut pieces of cloth are laid out before being sewn.
You can see the subtle curves on these two pieces, which are about to be joined together to an accuracy the thickness of a pencil line. And that means very precise calculations.
Up to a year ago, those sails were designed using this computer, a rare piece of antiquity. It's only 20 years old, built in the late 50s. But today, they're being designed on this micro. Not only is it a lot smaller, but it's much more flexible and even more powerful than this machine here. But looking at it, we can see some fundamental similarities. Similarities that exist on almost every type of computer you look at. They're overcoming the same types of problems, the problems of how to get data in. On this, it's done with a keyboard, and the output is either on a screen here or on the line printer. The little box here holds the memory and also the processor. It's very, very small. And the backing store is on a floppy disk, or a couple of floppies here, each one of these floppies holding 500,000 characters. And of course, it can be backed up by the old familiar cassette system. But let's look at how they solved the same sort of problems 20 years ago. Well, first of all, the data was input on punch paper tape, rather like this. It was produced on a typewriter-like device, punched the paper tape out, and then read on this reader here. This is the control panel of this computer, and commands can be issued by setting switches or even just dialing them through on this telephone dial. This is rather an interesting device. It's a meter which gives percentage program efficiency, whatever that may be. But once the computer's calculated its results, they can be output on this punch, once again, in punch paper tape form. But that's rather difficult to read, so in its turn, it's input into a teleprinter where the ordinary printout comes out. Well, that's the input, that's the output. The most fascinating part of this computer is this: the central processing unit and the backing store. Well, as you can see, it's a valve computer. It's a digital computer. That means it operates in binary. The numbers are carried in binary notation. In other words, a series of ons and offs. The backing store of this machine is this. It's a magnetic drum. It's rotating around here at 6,000 revs a minute, and on that drum is recorded the binary notation, binary numbers, and it's read off by these read heads here, one on each track. But how does information get from the paper tape reader, where it's read in, through this complicated maze of wires and so on, onto the drum and then be calculated on to eventually end up on the punch? Well, the secret is this: a gate. And this is a gate or a type of switch. It can either be open or closed, on or off. Again, binary positioning. And you can understand clearly how it works from this model of an AND gate. The signal will pass along this wire if that switch and that switch are both on. The alternate type of switch, there's 3 or 4 different types.